So today we will discuss the high frequency devices. High frequency devices. What are these? So at first you have to understand by high frequency devices, I does not mean that the device is undergoing oscillation with a very high frequency. It does not mean that. What does it mean? It means that the devices which can respond quickly by changing the frequency. That is how quick the device responds by changing the frequency of the input signal is based upon the high frequency devices. Now there are two possible high frequency devices, which are namely first one HBT, that is heterojunction bipolar transistor, and the second one is HEMT, that is high electron mobility transistor. Now the first point is, as I have given you, HBT, that is a heterojunction bipolar transistor. Heterojunction bipolar transistor. So the thing which we have already studied is bipolar junction transistor and field effect transistor. So at first we will deal with the bipolar junction transistor. This is known to us very elaborately, as we have studied elaborately about the bipolar junction transistor, as well as we have covered the field effect transistor, but our discussion is bipolar junction transistor. So what is this and why we have to record construction of heterojunction between them? Let us see. Okay, so at first we will revise the bipolar junction transistor, then we will proceed by pointing towards you that the requirement for forming the heterojunction between the uh, what we can say emitter and base region. Okay, so without wasting any time, let us proceed towards the bipolar junction transistor. So it is well known to you that in bipolar junction transistor there are three regions we have seen earlier. What are these? The emitter, base and collector. Okay, so out of which the emitter is highly doped or heavily doped, and base is very lightly doped, and collector is moderately doped. These are the doping characteristics, and the width characteristics are the emitter is moderate, base is thinner, and the collector is comparatively wider. Okay, so based upon these facts we can draw, this is emitter which is heavily doped. We have considered NPN transistor. What is the circuit symbol? This is the collector, this is the emitter. To signify NPN, arrow is given to this. This is emitter and this is base. Okay, so this is the representation for NPN BJT. So now we will study by this block diagram. So N plus region, base is made thinner and lightly doped, so we can say P minus, and thinner, so thinner, and the collector is wider, this, and moderately doped, so we does not signify any plus and minus here. And to make an ohmic contact, the terminal should be moderately doped. This. Okay. So what is the doping profile here? Here the doping is more, here the doping is very low, and here the doping is collected moderate. Okay. Okay. Now I have mentioned in qualitative factor to quantify this doping, we can say that in emitter region the doping concentration is about 10 to the power 18 per semi-cube. In base region, the doping concentration is about 10 to the power 15 to 10 to the power 16, 10 to the power 16 per semi-cube. And in collector region, the doping concentration is about 10 to the power 17 per semi-cube. Okay. Okay. Now, the base region is thinner. Okay. As I have mentioned. And the doping concentration is also low here. Now, if I want to ask you what is the seed resistance across these base, what will be the answer? By seed resistance, what does we mean? RS is nothing but the resistivity by the thickness. As because we know that the resistance is proportional to the area, cross-sectional area upon length, and the proportionality constant is nothing but the resistivity. So per unit cross-section, the resistance can be given by the seed resistance like rho by T. And rho is nothing but the conductivity, 1 upon conductivity, and this again the conductivity what we have studied earlier. If you forgotten, then I can remember you, make you remember. So NEVD, this was given. Now J is again sigma E according to Ohm's law, vector form of Ohm's law. So sigma is nothing but J by E, nothing but NE VD upon E. VD upon E means NE mobility. So sigma is nothing but NE into mu. So if we substitute this 1 by NE mu into T, okay, then you can clearly see from here that the seed resistance is inversely proportional to the thickness. As because the thickness of the base region is very low, the seed resistance will be very high. Okay, and this is in the base region. Again, since the numbered carrier concentration is very low, what we have studied that the depletion width is directly proportional to the square root of the carrier concentration. So by decreasing the carrier concentration, the the depletion width is also increasing. So the depletion width, if I mentioned here, the depletion width across the EB region will be very high, such that it will enter into the emitter region also. So this is known as the punch through region. Punch through region, which is present between the emitter base junction, and the value of the width, depletion width, is more or less 0.3 micrometer. I will let you know that the dimension of each and every what we can say, each and every component, the dimension I will mention in the next few minutes. Okay, so these are the case and the basic principle how does BJT works, you are known to this fact. And what is the term transistor signify? Means transfer resistors, that is the charge carriers move from the low resistance region to the high resistance region. So The low resistance region, why it is called so? Because we have to apply the forward bias at the emitter junction and we have to apply the reverse bias at the collector junction, collector base region. Okay. So these are all facts which is known to you, and by considering all these facts, the beta, that is the amplification factor, what we have obtained, the transistor amplification factor for the normal BJT, which can be expressed by a mathematical equation dNB upon dPe. I will let you know each and every term separately. This is Nd upon Na and Ni square B upon Ni square E. Now let us analyze each and every term separately. Okay, the conventional beta, you know that IC by IB, but here by considering the intrinsic parameters, we can get an idea about the current gain beta. Okay, now let us analyze each and every term separately. What is dNB? dNB is nothing but the diffusion length of electron. Diffusion length of electron in base region. It is clearly understood from the notation, but for the simplicity I have mentioned here also. Now dP, similarly what we can say for dP, this is nothing but the diffusion length of holes in the emitter. Nothing more serious about this. Okay, now what is the term ND? ND means the donor concentration of what? You should have to realize the donor concentration, the amplification depends upon what? The charge carriers are delivered from where? Emitter. So the current amplification should depend on the donor concentration of the emitter. Okay, upon Na means the acceptor concentration of base. Acceptor concentration of base. Okay, now what is Ni? Ni is the intrinsic carrier concentration. So what does NIB means? NIB means intrinsic carrier concentration in base, and NIE simply means intrinsic concentration in emitter. Okay, so these are all the terms which came into the picture for calculation of the BJT, sorry, beta for the BJT. Okay, now let us analyze this because we have already studied the IC by IB characteristics, but we are looking something more different from this. The how the current gain depends upon these parameters. Okay, so generally dNB by dV, which means the dNB, the diffusion length, dNB means the diffusion length of the electron in the base region is greater. Why? Because we know that the mobility of the electron is greater as compared to hole, so electron can traverse a greater distance as compared to the holes. So dNB should be greater than dP. Okay, dNB should be greater than dP, and as I have mentioned here, ND is greater than Na. So these two factors So these two factors is very much greater. Now the last factor, this we have to analyze. This simply means it should be greater than 1. And from our practical experience or from our practical knowledge, we know that for bipolar junction transistor the beta is nearly about 100 and the alpha, that is IC by IE, should be less than 1, nearly about 0.92. We have studied earlier. Okay, so from these two parameters it is clear that BJT, for BJT the current gain is very much high. But what does it control? The last term, how does the last term control on this dNb by dP and Nd by Na? The first thing that come into your mind is that Na is the intrinsic concentration. So it may be same for the base and emitter region, as because we are making the junctions, sorry, we are making these base and emitter with the same silicon, okay, same silicon material, as because we have studied the homo junction which is based on the same material. So the bipolar junction transistor is made out of the same material. So the emitter, base and collector, all are these created by the same material. So the intrinsic carrier concentration may be same. But if it is same, then there is no need to mention these terms also. But I have mentioned these terms. So there lies some significance out of this. So what does the significance arises? We have to analyze now. Now from the laws of mass action, what does you know that Ni square is nothing but Np, and which in turn is nothing but NcNv into some exponential of minus Eg by Kt. Eg is the band gap between the valence band and the conduction band. K is the Boltzmann constant, T is the temperature at which you are measuring. Okay. So NcNv at the carrier number density at the conduction band, number density of the charge carrier at the conduction and valence band respectively. So based upon this, now think the base region is doped moderately or very less doping is created here, and the emitter region is heavily doped. Okay, so the emitter region is heavily doped. Let us assume that this is the conduction band, this is the valence band for the emitter, and this is the valence band, this is the valence band, this is the conduction band for the base. As the emitter is heavily doped, the conduction band shifts towards this because of heavy doping. Because of heavy doping. Now realize that the band gap energy was previously like this, but the band gap energy now gets reduced due to the heavy doping at the emitter. So if we substitute the Ni square for base and Ni square for E, will it be same? Of course not. Then what will be this result? So all the term Nc and V will cancel, only the factor exponential will rise, and based upon this it will be exponential of minus the numerator it is base, so Eg we can say B by Kt divided by exponential of minus Eg, that is emitter. For emitter I have mentioned the subscript E, so it does result exponential minus of Eg for B minus of minus plus, so minus, okay, Eg upon Kt. Now Egb is greater than Eg, Egb is greater than Eg. Okay, so this term is clearly negative here. Exponential of minus delta Eg upon kT. Okay, so from this, from this this is nothing but ni square b by ni square e. So we can substitute this and get beta nearly about all these numerical factors into exponential of minus delta Eg upon kT. So whatever may be the numerical value which is very much high because of these factors, the exponential factor tries to reduce the contribution of this numerical factor, which in turn limits the gain of the transistor beta, so that we getting 100, not the infinite or not the huge term, sorry, not the huge value as compared to 100. This limits our current gain. Okay, so there were some persons which who are very much eager to get out the remedy of this and to find out the remedy for the limited current gain of the BJT, because we are very much greedy. Okay, for gaining something we are very much greedy. So to get something more than the what we are getting in conventional BJT, scientists were tried to find out the another combination of the BJT. How can we modify this conventional BJT to get some modified current gain? So for this they were found the heterojunction transistor, which can be made between two different elements. Now how can we make this? We will discuss now. Okay, now our main aim that we have mentioned earlier is HBT. So the first conditions or criteria to make some heterojunctions are the lattice parameter should be very close between the two junctions. The lattice parameter of the material should be very close. The next thing is the linear expansion coefficient should be very close between the two elements. And the third one is the electron affinity should be more or less equal. Now, out of these three parameters, the first one, that is the uh, lattice parameter should be very close, is very much important, as because if it is not so, then it will give out some strain in between them and the junction will get breakdown. Okay, this is the physical breakdown. Okay, the junction will not form actually. Now how can we form by the heterojunction devices? So for these we are interested by the gallium arsenide and aluminium arsenide. There are two composite semiconductor. These properties, why these are chosen, these are all known to you as because the previous lectures, and it is very much important material. Why? Because the lattice parameter, that is A, is very close. This is 5 5 5 so 5 6 5.6533, and this is 5.6605. So the lattice mismatch should be less than 0.1 something. Okay, whereas the energy band gap is 1.42 electron volt for this case, and this is what 2.16 electron volt. We are succeeding in achieving the minimum lattice mismatch, but the difference in the energy band gap is too much high, so we must have to reduce. Now what factor has limited our previous conventional BJT? That is this exponential term. What we are aiming to do, this sign should be positive, that is the energy band gap for the emitter should be greater as compared to the base. This is our aim. For aiming this, we have transferred from the conventional BJT to the heterojunction BJT to make the band gap energy between the conduction band and valence band of the emitter should be higher as compared to the base region. This is our aim. And for doing this, we have found two materials, gallium arsenide and aluminium arsenide, which has the minimum lattice mismatch, that is 5.6533 and 5.6605. So the lattice mismatch is less than 0.1, but there is a huge difference in the energy band gap. So we have to find out some possible ways to minimum this difference of the energy band gap. How can this be possible? By considering composite material. That is, if we reduce the composition of aluminium and increase some amount of gallium inside this material, which can we represent x and 1 minus x. So when x equal to 0, it gives gallium arsenide. When x equal to 1, it gives aluminium arsenide. So it is the intermediate. Now generally what we have chosen, x should be 0.23, so that 1 minus x is 1 minus 0.23, which is 0.77. Okay, so this is the composition which gives out the energy band gap, which is 1.72 electron volt, so that the difference between the energy gap is 0.30. Point 0.30 electron volt. Okay, so now you can clearly see that this sign becomes positive. Why? This was delta EGB minus delta EGE and delta EGE. Okay, what is delta EGE? Sorry, what is the energy gap for the emitter? What is the energy gap for the base? You are clear, but I will show you by drawing some cross-sectional view of these devices so that it will be better to understand. But you can see that that our aim is to increase the band gap of the emitter. So the emitter is chosen for this, and the base is made up with gallium arsenide. Now we can give you the cross-sectional view of this semiconductor. Okay, so uh, this is our emitter, which is heavily doped, made out with gallium arsenide. Emitter which is made out of gallium arsenide, heavily doped. this is our aluminium gallium arsenide. This is the P of gallium arsenide. This is N of gallium arsenide. This is also N of gallium arsenide, and this is semi insulating gallium arsenide substrate. Okay. So this is our emitter, which we can place a metal contact over here, ohmic contact. It should be ohmic contact. So this ohmic contact is made out from the gold germanium alloy. Why? Because it is a basic principle for the material science that for p-type semiconductor the ohmic contact should be made with the metal which have the work function less than the work function of the semiconducting species, and for inside it is reverse, that is the work function for the metal should be greater than the work function of the semiconducting species. So since it is inside, so the not aluminium, it is gold germanium alloy is taken as the metal contact to make the ohmic contact, because for n type the work function of the metal species is greater than that work function of the gallium n type gallium arsenide. Now this is the emitter, and similarly the base is made with this, where we can also make the metal contact, but here the metal contact is made out of gold zinc alloy. Similar reason, for p-type the work function for the metal should be less than the work function of the semiconducting p-type semiconducting species. So this. Now we can mention the thickness also. This is nearly about 0.2 micrometer thick. This is nearly about 0.3 micrometer thick. This is nearly about 0.15 micrometer thick. This is nearly about 0.5 micrometer thick. This is nearly about 0.2 micrometer thick. And this is the semi insulating gallium arsenide substrate. Now we can give you also the doping concentration. Here the doping concentration is 10 to the power 18 per semi-cube. Here the donor concentration is about 10 to the power 17 per semi-cube. Here the doping concentration is about 10 to the power 18 per semi-cube. Here it is nearly about 5 into 10 to the power 17 per semi-cube. Here it is also 10 to the power 18 per semi-cube. Okay. Now see, we require three probes: the emitter, the green color one is base, and collector. For collector, yes, this is the collector. It is also n type, so we can choose similar metal. This is collector, this is base, this is emitter. Okay. Now our purpose was to get the emitter to be high band gap energy and the base to be low band gap energy. So we are succeeding to achieve, we are successfully achieving this. Now we will see the similar expression here. for this case. So for this case, these terms remain unaltered, but okay, this term remains unaltered and this is becomes positive. So exponential of delta Eg by kt. Okay, so delta Eg is zero point 0.3 I have mentioned, and K is 8.617 10 to the power minus 5 electron volt per Kelvin. 8.617 10 to the power minus 5 electron volt per Kelvin, and at room temperature this is nearly about 300. And for conventional this can be taken as 2.5 more or less, and this, if we choose Nt to be greater than Na, then the beta you will calculate later, but here we are taking this to be 1 by 100. Why? I will let you know, because as we have mentioned here that Nd should be greater than Na, but here I have taken 1 by 100. The reason for this you will get. So if you substitute these values and calculate the beta, this is not for BJT, this is for HBT, then you will come out to be 2500 more or less, which is 25 times beta of BJT. So we are succeeding in achieving the high current gain by constructing the BJT from homojunction to the heterojunction. But it is the theoretical results that is in our hand. But practically what you will get, beta for HBT nearly about 30. Beta for HBT nearly about 30. Huge disappointment. So now you can realize if it is greater than 1, then this will gives much more value than this, some 100 times greater than this. Okay, so but our practical experience gives that the current gain is nearly about 30, so huge disappointment will be there. So to reduce this we have just considered 1 by 100, but instead of considering 1 by 100 we are getting 2500, which is very huge, but we are getting only 13 practical value. So there lies some mismatch there. So we will try to find out what is the mismatch or what is the cause for this low gain, what factor should limit this gain in the latter. So now theoretically we have achieved high current gain, but practically we have not achieved. Some factors limits this and we will discuss it later. So in this lecture you will get an idea about the necessities of the heterojunction bipolar transistor and the conventional bipolar junction transistor. What does the current gain limits, you are getting to knowing about this fact. So no more today. Thank you for watching. If you like, then you can hit the like button and subscribe the channel for more updates. Thank you very much.